So, good morning, everyone, and welcome to the second event of our live iTS4ZEB talks. I'm Giulia Righetti from the University of Padova, and I'm very glad to see you, many of you, joining again. Well, first of all, I'd like to thank you, everyone who followed our first session. We truly appreciated the participation and your interest, even in the following days of the event. For those who couldn't attend, the recording is now available on our YouTube channel, so you can easily catch up on what you've missed. Today, we'll continue this journey, moving from the theoretical principles behind the heat pumps to real-world applications, focusing especially on propane, on safety strategies, and how these technologies are being integrated in our project to support the European energy transition. Europe's transition towards sustainability requires more than switching to renewable energy, but it demands a complete technological shift in how we heat, how we cool, how we manage energy in buildings. So today we are facing a growing number of residential buildings, the yellow dots on the graph, and consequently a rising demand for heating and cooling. But at the same time, European regulations are becoming increasingly strict, especially the F-gas regulation, which pushes us to reduce the global warming potential of refrigerants to protect the environment. On top of that, we must integrate renewable energy sources, which are like intermittent and not always controllable, into the national and European grid. These trends bring several challenges to guide our work in this project and in refrigeration sector in general. So first, to ensure the compliance with the regulations while protecting the environment. Second, we need to guarantee safety, especially when working with flammable refrigerants. Third, we have to keep a high level of efficiency, even as the systems evolve. And then we need to boost the use of renewable energy sources, both in heating and cooling. And finally, of course, we need to achieve all of these while reducing energy costs for citizens. So in short, our goal is to make sustainable and accessible to everyone this energy transition. Heat pumps represent one of the most powerful tools for Europe's energy and climate strategy. They combine renewable energy with high efficiency. They can decarbonize buildings, of course, faster than the conventional systems. For instance, by replacing a traditional boiler, gas boiler, with a heat pump, we could reduce CO2 emissions by more than 70%. For this reason, up to date, we already have over 20 million units of heat pumps installed across Europe, with an annual growth exceeding 10%. But of course, we need to install many more heat pumps to reach the European goals that are set for 2030. But the questions still remain. why heat pumps? Why are they so efficient, and what are the limits for them? So let's go back to the fundamentals. A heat pump doesn't create or generate heat. It takes energy from a cold source, such as the air, the water, the ground, and it transfers it to a warmer sink, like, well, technical water loop or the indoor air of a residential building. So in other words, a heat pump moves heat. It absorbs heat at a low temperature and releases heat at a higher temperature. And that's why heat pumps are more efficient than gas boilers. Well, under moderate temperature difference, let me say, of the two sources, the heat pump efficiency is typically between 3 and 5. This means that for every unit of electricity, you can get from 3 up to 5 units of useful heat. On the other hand, with a gas boiler, you burn 1 unit of gas, and at the maximum, you can have 1 unit of useful heat. Of course, this efficiency depends a lot on the operating temperatures, on the geometry, that is heat exchangers, compressors, circuitry, and somehow also on the configuration. We can have air to air, air to water, water to water or ground source systems. In each case, heat is extracted at low temperature from the air, water, ground, and releases at high temperature either to ambient air or a technical water loop. And that's what makes heat pumps so efficient compared to traditional boilers. But in the real life, we really achieve the ideal cycle efficiency. We never achieve the real cycle efficiency because the theoretical efficiency is reduced by many practical factors. We have mechanical losses in the compressors, in the fan. We have fluidodynamics, heat transfer losses in the heat exchangers. We have defrosting cycles, for instance, part load operations to to serve the user. And sometimes we also have imperfect control logic or poor installation. And each of these contributes to lower the real efficiency. But there's another hidden factor, which is the refrigerant. Refrigerant may look a simple fluid, but its thermophysical and also environmental properties can affect the system's performance. The history of refrigeration has always been a balance between efficiency, environmental impact, and of course, safety. We started with the first generation of refrigerants. We started with natural refrigerants like carbon dioxide, ammonia, propane, which means the available fluid. Available, but very difficult to handle sometimes in terms of safety. Then came a second generation, CFC, HCFCs, very stable, not flammable, very high in efficiency, low in price, but devastating for the ozone layer. So after the Montreal Protocol, we moved to HFCs, no zone depletion, but unfortunately, extremely high in global warming potential, as you well know. So the next stop was HFOs, marketed as the future low GWP alternatives. Still good efficiency, higher in price, but as I think many of you already know, they could degrade into PFAS compounds, raising new environmental concerns. So we are now back to the roots. We are at the fifth generation, or maybe we are cycling back to the first generation of refrigerants. Natural refrigerants again, CO2, ammonia, propane, all with near zero GWP, but each bringing us specific safety challenges. Just a brief insight on this hot topic, PFAS. They are a large, very large group of chemicals, of fluorinated chemicals used in several products like food packaging, cosmetics, textile, and also refrigerants. Because, well, for their environmental properties. But they are also called the forever chemicals because they don't break down into the environment and they accumulate as is in the soil with several risks connected to health and ecosystems. The European Union now is moving to ban them with new regulations progressively restricting the production and also the use in many sectors. So this, if these PFAS are going to be banned, probably a lot of fluorinated refrigerants could not be used anymore. This shows how the European policy is moving fast and consequently how the refrigeration industry must innovate quickly to stay aligned with these upcoming environmental regulations. Thermodynamic and chemical screening has shown that the most efficient refrigerants are built mainly from three key atoms: chlorine, fluorine, and hydrogen. And each of them influences the behavior of the fluid and its environmental impact in different ways. For instance, if we add chlorine, the refrigerant becomes toxic and it damages the ozone layer. So chlorine-based compounds have been phased out. On the other hand, if we add fluorine, the molecules become very stable, but they become stable also in the atmosphere for a very long time, leading to a high global warming potential. So the only remaining option is hydrogen, which gives us excellent thermodynamic performance, no environmental issues, but it makes the refrigerant flammable. So when we remove chlorine and fluorine for environmental reasons, what remains are only flammable refrigerants. And that's where our research has to move toward safety design. Once we understand with this chemical background, it becomes clear why propane, a flammable refrigerant, stands out. It's one of the few refrigerants we have which combines very low global warming potential with excellent thermodynamic and heat transfer performance. That's why it's now considered one of the most promising alternatives, for example, to the classical R410A for future heat pumps and air conditioning systems. Simulations and models like the one presented in this graph say that propane can offer similar or sometimes even higher efficiency under theoretical, so the ideal working conditions. The real challenge, of course, is how to manage its flammability safely without compromising the efficiency. And that's exactly what we are addressing in our Life iTS4ZEB project. In iTS4ZEB, we work under one guiding principle: efficiency, but without compromising safety. And to achieve this, our design includes many points, like limiting the refrigerant charge per each circuit, ensuring control, air exchange through fans and vents, or using leak detection and safety systems. And of course, why not optimizing the layout to avoid stagnation zones? So the core idea is to shift the focus from not avoiding leaks entirely, which is almost impossible, but to manage leaks safely. So our ventilation strategy ensures that even in the case of a leak, propane is controlled, is directly outwards, never into the indoor environment. And to verify this design, we built a simplified 3D CFD model, a fluidodynamic model. These simulations confirm that the ventilation strategy effectively prevents flammable concentration inside the living room, inside the building, inside the environment where humans live. So these results then will guide the design recommendations and safety protocols for the commercial deployment. Of course, beyond the refrigerant itself, iTS4ZEB also looks at system integration. Our goal is to make heat pumps not only safe and efficient, but also smart, flexible, and powered by green energy. So we are developing a hybrid system that combines heat pumps with thermal storages, specifically latent thermal storages based on phase change materials. And this integration shows that we can have a lot of benefits. For instance, we can store the excess of heat produced when the green energy is available. We can reduce the compressor cycling, we can shift the demand in time, and also we can support and balance the smart grid. This concept is very relevant for near zero energy buildings, where flexibility and self-energy consumption are key. So looking forward, the future of heat pumps will combine, I think, three main points. Refrigerants, eco-friendly refrigerant, low GWP eco-friendly refrigerants, an advanced safe design, and last but not the least, smart system integration. Because we want to demonstrate that green can also mean high performance. And well, we are building a pathway in this project representing the complete transition chain. We are moving from science to test, to field test, to developing a new technology into market and then also policy. In other words, we are turning the energy transition into reality for, of course, residential air conditioning. With this, I think we've reached the end of today's session. I hope this overview helped to understand how our project is turning research into practical innovation. In fact, if you can see inside the partners, I want to thank you all. You can find companies, very large companies, but also universities and research entities. Before we close, I want also to thank you all for joining today and for the attention you've given to this second event of our talk series. If you'd like to know more, you can visit our website, iTS4ZEB.eu. You can follow us on our social media or subscribe to our newsletter to stay updated to the project activities and all the upcoming events. We'll meet again soon for our next webinar at the end of January, which will focus on life cycle assessment and environmental impact evaluation, which is a key step in understanding the full sustainability chain and the full potential of these technologies. Finally, we are open to the Q&A session, so feel free to write your questions in the chat and we'll be happy to answer them. Thank you again for your time and your participation.